Hello everyone, my name is Martin Skarsaune. I work as a developer for a company called Contega in Norway. I really enjoyed this conference, lots of new nice things to know and even looking into the future. But right now we're going to do the exact opposite of that, because we're going to look at some good old technology. And when I say old, this stuff existed before I was even born. So the title of the talk is Small Lambda Talk. So we will look at lambdas, but perhaps in a bit different angle than what you've been used to, because a lot of the push for the lambda this recent years has been focused around functional programming. But now we will look at lambdas within object-oriented use. And so comes the first and the last word of the talk, Smalltalk. So we will then look into the Smalltalk programming language. Do we have any grumpy old Smalltalkers in the audience? Okay, good. So we're going to have to learn a new programming language, and the good news is that this is really simple. So I think within this presentation you should get quite a good feel for the language. As an illustration of that, I put up all the reserved words there are, which I guess you would figure out quite easily. And as Java developers, you're used to quite a lot more than that. Now the main concept of Smalltalk, I have a quote from the creator of Smalltalk, Alan Kay. He says that Smalltalk's design and existence is due to the insight that everything we can describe can be represented by the recursive composition of a single kind of behavioral building block that hides its combination of state and process inside itself. Well, this is of course objects, and then it goes on to say, and can be dealt with only through the exchange of messages, which we will look at what is. So the claims here is that this is enough to express absolutely everything we need. So the first thing we need are objects. And so we say everything is an object. And what does that mean? There are no primitive types. Even nil is an object. So whatever reference you have in your application will point to an object. There are also no void methods, so whatever you do will produce an outcome which will also be an object. And then the second part, the messages. What are messages? There are three kinds of them, but that's simply different syntax on the VM, and conceptually it's exactly the same thing. It might sound kind of exotic with messages, but you can just think of it as methods and method invocations to map it to a more common concept. Now the simplest form of a message is what's called a unary message. And a unary message has no arguments. So if we give an invocation example, we just write the message identifier. So here we say we send the message negated to 2. And I put some Java-ish syntax beside to make it easier. On the implementation side, since it's dynamically typed, the signature is exactly the same as the sending syntax. And in this case, it's implemented by a single statement. The caret at the beginning means return, or in Smalltalk terms, answer. So we say, well, answer 0 minus myself. Second kind of message is the binary message. It has exactly one argument, and the special thing about it is that the message identifier will be one or more special characters instead of a text identifier. Invocation example. Here we see we have the receiver on the left-hand side, then the identifier, and then the argument. So we say we send the message equals to A with argument B. And on the implementation side, again, the signature is the same. And you see that in Smalltalk, as in Java, the default implementation of equals is an identity comparison. Then we have a third kind of message, the keyword message. It has one or more arguments. And when each argument is separated by a keyword. We'll see an example of this. So also, when you call it, you qualify each argument with a keyword. So what you see here is one message send. So we send the message at put to A with arguments 1 and 1. On the implementation side, again, same signature. And in this case, we delegate to some other object. Now I said there were no void methods. And so what will happen here, because we don't have an explicit return, is that the object itself will be returned. Okay, so now we have objects, we have messages that you know from other programming. But how can we make more sort of fundamental stuff? So we will look at how we achieve conditional processing. Right, so to do any sort of logic, you need a Boolean concept, right? Now the trick in Smalltalk is that the true and false values are in fact singleton instances of dedicated subclass, class true and class false. And we'll see how this is used. So as an example, we have a tree structure, and we want to write a recursive method to return the root of the tree. And each node can access its parent by sending parent message, or nil if it is the root. So if we then try to implement this in Smalltalk, I will walk through the code here. First we send the unary message, the helper method self-parent, which will then either be nil or the immediate parent. And then we do send a binary message with the argument nil. And as you recall, equals will then either return true or false. And then there's a keyword message, and we see something a bit special about the syntax here. So this is the third component we need to build these things. This is referred to as blocks. So when you evaluate a block, the code is not executed. Instead, you get an object that refers back to the code, just like a Java Lambda. So if we assume that within the first few runs, the parent is not nil, so false will be the receiver. In this case, if true if false is then overridden in false, so it's a keyword message, it has two arguments, one true block and one false block. And in the false case, we send the message value to the false block. And what happens then is then the block is executed. So we make a recursive call, and eventually it will be true, and this will happen. So just to look at this, now we have, just using object, messages, and lambdas, we have created something as fundamental as an if-else. And there's some nice characteristics to this. Both the Boolean receiver and the arguments are first-class objects that you can parameterize, send references to, and so on. It's also one expression with one return value. So if you chain these downwards, it's still just one expression. And we can look at, okay, how can we refine this even more? There's some nice effects of the fact that nil is an object. In the last example, we did the equals comparison with nil. We can express even more content that we don't just check for anything, we want to check for nil. In this case, we can make use of the fact that nil is an object. So there's a method called isNil, which is false for any object, but true for the one nil instance. And in Java, you can quite easily have the same sort of nil semantics attached with the optional in Java 8. Another nice effect is that we saw that the equals was an identity comparison, and that means that the only object, if you implement your equals methods properly, the only object that could ever be equal to nil is nil. So when you compare objects, you don't need to worry about the order. This is also something you get with optional in Java. And finally, since these parts to make these low-level things are so easily accessible in Smalltalk, you have very many specialized sort of constructs. For instance, we have something called ifNil, ifNotNil. And for all objects, this has two blocks, one block for nil and one block for others. And here we see something special. We send the message value with an argument to the block. And the value, the receiver will then be parent in this case. And here we see a block with an argument. So this is like a lambda with one argument that would pass back. So if you don't get all the syntax and so on, that's not so important. The important part is that since the building blocks are so easily accessible, you would typically make, for instance, some domain-specific testers, or if you find out that you're making the same sort of comparisons over and over again, or same sort of tests, you can make some specialized things for that in your library or in the application. And then if the underlying logic somehow changes, you can easily track this down. So that's sort of the idea. As we're looking just at the low-level stuff with the booleans, there's other use cases for this. So for instance, when you have a shortcut boolean operator, as you know, when you do the AND case, if the left-hand side is true, you should then evaluate the right. But if it's false, you don't have to, right? So in that case, in Smalltalk, you would also need to rely on blocks to get this behavior. So the implementation then is that if the receiver is true, we will evaluate the right-hand side. If it's false, we can simply return ourselves. So any suggestions on how you would implement OR? For instance, for true? Exactly. And for false? Yes. So for true, you return yourself. For false, you would evaluate the right-hand side. And another example is not. This does not require lambdas, but it's also quite elegant. How would you implement not for true? Yes. And for true, you return false. So one nice thing in Java 8 is you have this functional interface called predicates. So there you have the test method, where you would then use a lambda expression to express some sort of condition. But you also have some default helper methods that allow you to do the same kind of logic, like AND and OR and negate. So if you want to do this Boolean logic in Java 8 with first-class objects, you have a way to do that. So I've not been entirely honest with you so far. So just make a simple point that in most Smalltalk compilers and VMs, the stuff that I showed you will not actually happen. It will be inlined, but still it's present, that is true, and sometimes it will fall back to that. So what can you learn from this ancient stuff? Well, I think the main idea of Smalltalk is that the language can be really minimalistic and with generic enough building blocks so that you're able to express anything that you would typically require language syntax for in other cases. So I showed you really simple stuff. The same goes for, we saw branches, but also various kind of loops. There's a big variety of loops. Also exception handling is done in this matter. And if for instance, if you're working on some domain-specific language, you're doing some sort of interpretation, I think it could be a good idea to look into some of the Smalltalk class libraries, because you find some very elegant divide and conquer object-oriented strategy there. Also, for instance, if I wanted to create a programming language where you would express things in Norwegian for my kids, I could do that quite easily with Smalltalk. So it's a sort of just trying to show you some ways that you can use this to express very powerful stuff. So with that, I would like to thank you for your patience. And as another example of a language where you can do things in code that other languages would require changes to the language, I will show some calculation stuff in Java later. Thank you.
you engrave it. Let the bayou melt in the mud. Dip your toe in the mud. Stir it with your foot. Across the muddy water. Sisters and brothers. Let the bayou melt in the mud. Dip your tongue in the dirt. Slide across the surface. Across the muddy water. See what it tastes like. The mamas and the papas are still a strong match. The brothers and the sisters are still a strong pack. The movers and the shakers are totally right. And me and you are still a fact. The mamas and the papas are still a strong match. The brothers and the sisters are still a strong pack. The movers and the shakers are totally right. And me and you are still a fact. Slide your legs in the mud. Knee deep. Let the grease work your skin. Gently. Let the bayou melt in the mud. Slide your foot in the water. Strangling your ankles. Move it side to side. You know when you hit the spot. You know when you hit the spot. Let the bayou melt in the mud. The mamas and the papas are still a strong match. The brothers and the sisters are still a strong pack. The movers and the shakers are totally whacked. And me and you are still a fact. The mamas and the papas are still a strong match. The brothers and the sisters are still a strong pack. The movers and the shakers are totally whacked. And me and you are still a fact. It's gotta be down there somewhere. It's got to be down there somewhere. It's gotta be down there somewhere. You know when you hit the spot. It's gotta be down there somewhere. It's got to be down there somewhere. It's gotta be down there somewhere. You know when you hit the spot. The mamas and the papas are still a strong match. The brothers and the sisters are still a strong pack. The movers and the shakers are totally whack. And me and you are still a fact. The mamas and the papas are still a strong match. The brothers and the sisters are still a strong pack. The movers and the shakers are totally whack. And me and you are still a fact.
Et sprog mere, ikke?
until. All right. Hello, everyone. My name is Martin Skarsaune. I work for a consultancy company in Norway called Contega. And today I would like to talk a little bit about calculations in code in general and how I see Scala as a good platform for that. The topic is very big, so we don't really have time to go into too much detail. So my idea is to just, scratch the surface and give a little taste of how you can express things and try not to go too much into details and implementation. Just very quickly, I will go through the situation typical in Java. The really basic stuff, we have the integer types that provide exact representation within the range. And you have the compiler and the typing rules will then allow you to combine them with widening conversions. Then you have the floating point numbers, which are approximate representation of numerical values. So they can be good for things like scientific applications where it's an approximation of reality anyway. But you should never use them for monetary amounts. And here also you have static rules that allow you to combine floating point types and integer types. On top of this, we have the boxing types, the sort of object types. They're immutable as proper value objects. And the most convenient way to do calculation is to go via primitives with unboxing. And there you have the same semantics as for primitives. And if you want to, you can then box them back in again. And finally, we have some more complex number types. Big integer, big decimal, that you need to call methods to perform calculation. And I think my objection is that I feel the number hierarchy in Java it's very cumbersome to mix things and convert back and forth and so on. And just to follow up on the talk I just did, as a reason why I'm not satisfied with that is I used to work in Smalltalk, where you have some different characteristics. Numbers are objects, you don't need to box. You have binary message selectors, so you can express things with symbol, not just method names. You have very good built-in decimal support, as in COBOL. Overflows are taken care of. You have what's known as precise division, and it's very easy to extend the model. So I've looked at Scala, and I think Scala has many ways to achieve the same. And at first sight, the Scala type model looks more or less like Java, that you have, I've just put up the main types, you have some really basic primitive stuff, and you have some sort of more complex stuff, and there's separate places. We'll see what Scala does to overcome this divide. So first we'll focus on decimal calculation. How do we represent decimals in computers? Well, you have an integer value, which is then a big int, so that it can grow as much as it likes. And then you have a scale, and the scale tells you where the comma lies. Or you can think of it as a fraction where the denominator is some power of 10. And scale is important. You should always be aware what scale you have. Most importantly, to make sure that you have enough precision in the calculations you do, but there could even be some regulations in the domain you're in or something about these calculations. Now, how do we declare decimals? In Smalltalk, you just do this. You say, I want decimal 2.5 with scale 2. In Java, you would achieve the same by saying new big decimal and then a string constructor. If you don't like strings or want more sort of compile support, you could use a double and then set the scale. In Scala, we can simply do this. You don't get the scale right, but we'll come back to that. Now, what just happened here? You see that this is the highlighting is from Scala IDE, so there's it's underlined. We'll see why that is. what you just saw is what's called implicit type conversion. So when you have a source type that should fit into a target type, the compiler will look for an implicit function that does that conversion. So in the object Scala math big decimal, we have double to big decimal, an implicit method that takes a double argument and will return a big decimal. So if I clicked that literal, the IDE would take me here. Okay, so now we have a decimal and we want to do something simple with it. We want to multiply it by 100. In Smalltalk we can do this. I could use a decimal literal, but there the dynamic type system dispatches back and forth and figures out the correct way to do this. If we wanted to do it in Java, we would then have to construct a new big decimal argument, and then we call the multiply method. In Scala we can simply write it like this. And we'll look at how this is possible. First of all, you're able to use special characters as method identifiers. We can use the conventional arithmetic operators, so we can even use Unicode to have mathematical symbols. So here we see the method multiply with just an asterisk as the method name. And then we have what's known as infix notation. So we could make this method call by a dot and method name and parentheses around the argument. But you can also just write it with the receiver, the method identifier, and the argument. So it looks like a sort of language built-in feature. So you also saw in this case, it's underlined. So the argument is actually an integer literal, and then again, the compiler will look for a converter that's able to convert from integer to big decimal. You could even write an integer literal to the left, and then multiply with a decimal. And then it will look for a method that implements multiplication with the big decimal argument, and we would know that the receiver would then have to be converted. So just to sum up, we get natural syntax with operators and literals. The big decimals are then interoperable with other number types, and very important, we do not have to change int or double in order to achieve this. So if you want to do some real math stuff, there's an excellent framework called Spire Math. And they have what's known as generic algorithms. So they have implemented algorithms that you could plug in your own number types in. I found the functional community very good at this with algebras and things like that. I will also provide some references at the end. So some really clever stuff in there. They also have extended number types, which we'll see some examples of. And they also have macros that allow you to write Scala syntax that is then pre-processed in the compilation process. So, a Java example, we multiply 1,000,000 by 1,000,000. Does anybody know the result? Is it a trillion? You see, these are not long literals, it's int literal. So the answer is this. So can anybody tell me what just happened? Yes, you even know more details than me. Okay. So we see an overflow. Now what can we do about this? Like in Smalltalk we didn't have this problem because you had small integer and large integer, and the VM would ensure that the result was sufficient to hold the result. In Java you have some libraries that you can use, but in the VM as such there's no support for it. So we look at some of the types in Spire. You have what's called a SafeLong. And the SafeLong is able to detect overflow and ensure an optimal representation. So I have to raise the stakes a little bit because the smallest unit is a long. So I begin with a trillion and I assign it to a value that I say it should be of type SafeLong. And that will be an instance of SafeLong long. But then if I multiply that by itself, the result will be a SafeLong big int. But then again, if I take that result and divide it by something that fits into a long, the result will be a SafeLong long. So you can use this without having to worry about overflow. Okay, over to division. What is 2 divided by 3? Is it 0? Is it this? Perhaps this? Yes, exactly. It's 2/3. So there we have, first maybe show the Smalltalk case. Since Smalltalk is dynamically typed, if you divide an integer by an integer and there is no remainder, you will get an integer result. If there is a remainder, the result will be a fraction. And since it's dynamically typed, you can use this interchangeably. And if you later then should multiply it by something which does not give a remainder, it will turn back into an integer. So Spire has the most generic number type is real, which can then, as in mathematics, real sort of represent all kinds of number, which as high precision as is possible. So if we look at an example of this, we create a real, and this will be an instance of real exact, and then we divide it by something that gives a remainder. And now it's represented as a rational. Actually, the first case is also rational, but where the denominator is 1. And then if we multiply it by 3 again, we get the rational with a remainder of 1. Now, what happens if we combine this with a number that is not exact, but an approximation? Well, the real will then try to maintain as much accuracy as possible, but it will contain information to show that this is not an exact representation, but as close as they can manage. So let's try to do some very simple Mickey Mouse conversion of our own. We create a class called double syntax, which is a wrapper around the double value. Then we create a method called scaled, which takes an int argument and should then return a big decimal of that scale. So it will take the double value, convert it to a big decimal, and set the scale. Then we create a second method, which we call I, and the I will return a complex number. That's a number type we borrow from Spire, where the imaginary part is the double value. And then finally, we create an implicit converter from double to double syntax. And this would allow us to write code like this. If you recall, Scala and the big decimal already had support for allowing us to use number literals and turn them into big decimal, but we were not able to control the scale. So now we can instead say 2.5 scale 2. Now we no longer need to type it as a big decimal, because that's given from the return value. And we're also able to control the scale. And with a complex example, with the method I we just made, here the compiler has to do quite a lot. It sees the method I and looks for a way to convert a double to something that understands I. And then it will look at the other number and see, okay, on the right hand side we have a complex, and then it will use the conversions in complex to convert the first double into the real part of this complex. So now we can write quite normal and very sort of natural syntax for complex numbers. So as a conclusion, Scala gives you the opportunity to use very natural syntax for calculations, and the implicit type conversions allow you to make these things work together and extend on what exists already. And as Spire demonstrated, this allows for new number types and new calculations to be added. Some references, I will put the presentation on SlideShare, so you can find everything from there. And with that, I would like to thank you for your attention.